Today I'm going to talk about two topics. The first topic is about Fourier series for 2T periodic function, and the second topic is about the Riemann Lebesgue lemma. So let's first talk about the first topic. So let G be a 2T periodic function. Then we can define a 2T periodic function fx as gtx over pi. To see that it is a 2-pi periodic function, we just compute f2 pi plus x, which is equal to g t times 2 pi plus x over pi. And this is equal to g 2t plus tx over pi. And as g is a 2-pi periodic function, we see that it is equal to gtx over pi, which is equal to fx as we defined. So why are we defining a 2-pi periodic function? It is because we have defined what a Fourier series for a 2-pi periodic function mean. So as we previously defined, we know that fx have a Fourier series like this. And how can we recover the Fourier series for g? Well, we see that f pi x over t is equal to g, so we can simply do a change of variable and we replace x by pi x over t. So we get that gx is equal to f pi x over t, which is we can replace the x in the Fourier series of x here. And therefore we get that the coefficient here should be equal to the following form after the change of variable. And I will prove the case of an, and other cases I will leave it as an exercise. First of all, before the change of variable, an is given by this form. And after the change of variable, we get that the x is replaced by pi x over t. And for this term, d pi x over t is equal to pi x over t. And the pi here and the pi here will cancel out. And we are left with 1 over t here. Also note that the upper bound and lower bound are also replaced. And therefore, we get the expression for an. So, after introducing the 2T periodic function, we will introduce another important lemma for the theory of Fourier series. So, if we observe carefully on the Fourier coefficient, we can see that they tend to 0 as n tends to infinity. And we find that it is in general true. So let's state the theorem first. Well, the theorem says that the Fourier coefficient of a 2-pi periodic function, which is integrable on the closed interval negative pi to pi, converges to 0 as n tends to infinity. Well, we need a lot of ingredients to prove this theorem, so I will leave the proof in the next video. So I'll see you in the next video.